Let's look at problem number 6. We want to give the basis of the column space of A. Well, we need to put A in row echelon form. And to do this, we need to zero out the entry in the second row, first column. The first row will remain the same, so it will be 1, -1, -2, 1. And the second row will become 1 plus -1 is 0, 2, 0, 1. There are 2 pivots and 2 free variables. And so when we want to give the basis for the column space, it's created from the pivot columns. And so one basis is the vector 1, 0 and the vector -1, 2. And remember, this basis isn't unique, but this is 1. Now, we need to give a basis for the row space of A, which is the column space of A transpose. So the basis vectors will be of size 4. And again, we can read them from the row echelon form for A. So one of the basis vectors will be the vector 1, -1, -2, 1, and the other will be 0, 2, 0, 1. And again, these are not unique. If we recognize that the rows in A were linearly independent, we could actually have used the original rows also to describe a basis for the row space of A. But we can read another basis from the row echelon form of A. Now, we want to find 2 linearly independent vectors in the null space of A. Well, to do that, first again, I use the row echelon form of A to describe 2 equations that the vectors must satisfy. So the idea is A times this vector would have to be equal to 0 if it's in the null space of A. And that means, from the row echelon form, that this vector, again, which is of size 4, would have to satisfy that chi sub 0 minus chi sub 1 minus 2 chi sub 2 plus chi sub 3 would have to be equal to 0 from the first row. And the second equation that must be satisfied would be that 2 chi sub 1 plus chi sub 3 would have to be equal to 0. Now, if we want to find linearly independent vectors in the null space, what we do is pick some convenient values for the free variables. And so typically we pick one of the values to be 0 and the other value to be 1, and switch it because those are convenient values in order to find independent solutions to the equation AX is equal to 0. So let's get to it. The approach is going to be to first set our free variables to some convenient value. So we'll say, let's let chi 2 be equal to 0 and chi 3 be equal to 1, and then switch it and let chi 2 be equal to 1 and chi 3 to be equal to 0, and then solve to find what the values for chi 0 and chi 1 must be for AX to be equal to 0. So in the first situation, we would have chi sub 0 minus chi sub 1 plus 1 is equal to 0. And we would also have 2 chi sub 1 plus 1 is equal to 0. If we substituted a 0 for chi 2 and a 1 for chi 3 into my equations, we find by backward substitution that means that chi sub 1 must be negative 1/2, and chi sub 0 would have to be, well, let's see, chi sub 0 minus a negative 1/2 plus 1 has to be equal to 0. So chi sub 0 would have to be equal to negative 3/2. So one vector in the null space of A must be negative 3/2, negative 1/2, 0, 1. Let's find the other. In this case, we would have chi sub 0 minus chi sub 1 minus 2 is equal to 0, and 2 chi sub 1 is equal to 0, since chi sub 3 is equal to 0. Solving again using backward substitution, we find that chi sub 1 would have to be equal to 0, and chi sub 0 would have to be equal to, well, that's chi sub 0 minus 0 minus 2 would have to be equal to 0, so chi sub 0 would have to be equal to 2, which means another vector in the null space would have the components 2, 0, 1, 0.